are we talking about when we say squared? The second power, right? So now suppose that I tell you when x equals 2, y equals 20. Find y when x equals 4. So imagine what happens when you double x. Do you expect that you're going to double the value of y?
So x will represent what? The canvas?
X in this case would represent the side of a square, for example. Let's say that I had
A canvas.
that was a square. X
Okay.
could be the length of the side, and y could be the amount of paint I need.
Okay, 20 ounces per se, or?
So let's just say, yeah, 20 ounces paint. So how much would I need to paint a canvas that was 4? 4
Okay.
by 4. 4 inches by 4 inches. 4 feet by 4 feet. Don't worry so much about context just yet. Just understanding the mechanics of the problem. First, you need to write your equation. Y varies directly as something begins like this. Y varies directly as something. Is this correct? Y varies directly as x.
No, it should be x squared, right?
It varies directly as
Oh, yeah.
the square of x. You have to be able to see the square of x means x to the second power. All right, so now you have a slightly more complicated equation to solve. Not too much, but a little more complicated. So go ahead and find k. Try to finish the problem right now while I do the attempt. Going to place of x? 2. All right. So this is going to be 2 times 2 is 4. 4 times k is 4k. So now I divide by 4, and we get k equals 5. Are we finished? No. We just found k, so now we can plug k back in here. So we have the equation y equals 5x squared. That's the equation that establishes the relationship between y and x. So now when I tell you that x equals 4 and I want you to find y, all I need to do is take this 4 and do what with it?
Square.
Plug it in place of x. So y is going to equal 5 times something squared. What is that? Something? 4. 4 squared? 16. 16. So this would be 5 times 16.
80.
And that gives you?
80.
So as you can see, when we doubled the value of x from 2 to 4, the amount of paint didn't double, it went up by 4. 4 times 2 is 80, but this is as far as you need to be at this point. I have now an application that I can give you for, that's a little more standard, the one that you're going to see in your activity. And that's the effect of gravity on a free-falling object. For example, if I take the marker, you may not see it, just with your naked eye here, but the marker doesn't fall at a constant speed. It picks up speed the more time that, if I was to, a marker may not be a very good example to use here. If I was to stand in a tower, for example, let's say a building that was 100 stories high. If I drove the marker because of air, there would be a lot of air resistance. But let's say I can get a ball bearing, something that's heavy and small and compact and doesn't experience a lot of air resistance, and I drop it. What you would notice, right, is that the ball bearing begins to pick up speed with time, and therefore, the distance that it covers in 1 second here is not the same distance that it covers in 1 second right here.
It increases.
Right? So we can say, here's an example of a direct variation. If we let d equal the distance a free falling
But doesn't it reach a terminal velocity where it just reaches a max speed?
What is that?
Doesn't it reach a terminal velocity when it reaches a max speed?
In reality, it does because of, in other words, it doesn't, number one, we don't have an infinitely long, a tall building. So there's going to be, at some point, it's going to hit the ground, right? It's not going to pick up any more speed. I would tell you, if you were to jump off an airplane, you would experience that. But of course, you're not exactly free falling unless somehow they could create some kind of vacuum room when there's no air, to hold you up. Then this thing theoretically would keep, until a force acts on this body, gravity would keep pulling it faster and faster and faster. But in reality, you're correct that the objects don't fall according to this rule because there is air and there is resistance. But we're going to just take an ideal situation. We're going to consider free falling to mean we're going to disregard the resistance of the air. We're going to assume that this thing can fall without any forces other than gravity acting on it. Distance a free falling object travels. And we're going to let t, the number of seconds the object has been falling. So there's a relationship that we know by experimentation, right, between the distance that an object falls and the time that it's fallen, and we say that d varies directly as the square of t. D varies directly as the square of t. So again, imagine that you take this ball bearing to a very tall platform and you release it. I'm going to give you some information. Two seconds after being dropped, the object has fallen 64 feet.
It's gonna be 128.
So the question that I want to ask you now is, what distance will the object have fallen after 4 seconds? So from the moment you drop it, if you were to measure, okay, here it is, and somebody takes a snapshot of where it was 2 seconds after you dropped it and you measure that distance, it travels 64 seconds. What if you let it go another 2 more seconds? Do you think it's going to be 128 feet? You think that if you give it another 2 seconds, it'll be another 64, so that'll be 128? So work it out. Let's first translate this right here into an equation. Solve for k, and then try to answer the question here, how far this object has fallen after 4 seconds.
1024.
So notice it's a little different from this problem in that I don't give you x equals this and y equals that. You have to figure it out from the context of the wording here.
It's 1020. 20.
Let's start with this part right here. D varies directly as the square of t. Can someone help me out with that? D equals
K.
K t squared. Very nice. That's what varies directly means. D equals K times something. How do I translate it into a variable? What does that mean? Which variable is that? We have two variables. We have D and T. Do you think this is a measure of time or a measure of distance?
Time.
Time. So what does this say?
T
T
equals 2.
When T equals 2, blah, 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 64 feet. What is this?
Distance.
So what do I say?
D equals
D
64.
64. That's what you use now. When the time equals 2, the distance is 64. So go ahead and find K using those two values there.
It's almost like the computer memory. You go
How's that?
164, 128, 256, 512.
Oh, you mean that,
And-
I'm not very computer savvy, but yeah, I realize that they do have this.
So it follows that pattern. Is it Moore's law?
No, I'm not sure. I'm not sure on how computer memory is allocated. I would imagine it has to do something with binary numbers, zeros and twos and powers of 2. But I'm not really certain how. That is one area where I'm hopefully ignorant. Let's plug in these two numbers to figure out K. What is D?
64.
And what is T? Now don't forget the square. A lot of students set out the right equation here, and when they go solve for K, they forget the exponent. So be aware of exponents. So this is going to be 64 equals 4K. We divide by 4. And what do we get for K?
16.
All right. So what's our equation? Once we take this K and plug it back in here. D equals
16. 4.
16 t squared. That's the equation. Yes?
Is there a shortcut?
But the shortcut would be that you can write the equation like this. D over t squared is a constant. So that would be one shortcut. Another way that I don't want to confuse you with this, I'll show you in a moment a slightly different way of doing this, but this would be the way that I'd advise you to do it because it's very uniform. I know it seems like a lot of steps. I mean, you can skip a couple of steps. From here, if you go directly to this, and if you skip that and just put in the value of t, as some of you just told me, right? What are you going to plug in for t? 4. When t equals 4, we're going to figure out the distance. To Ulises, I'm not sure that I have any real shortcut here to. Is that right? 16 times 4, I just multiply? Squared. That's right. I gotta remember my exponent here. So can someone tell me what it is?
255.
What is it? How about that? The first 2 seconds it only went 64. But in 2 more seconds this object had already fallen 256. Is that what you said? 256? What units?
Feet.
Feet. That's right. 256 feet.
Will ever be like t squared?
Not in this context because distance is not measured in square. But let's say I had a problem where I said the area of some object varies directly as the radius or something. Then yes, if I'm talking area, there may be a chance that the units we're talking about may be feet square. So just be aware. You only need to worry about units, by the way, when you have a real problem like this. If you have one of these things like that, where there's no context, don't worry about units. Units are not going to matter. Just be aware of what the variables represent. Yeah, that's something that people that do things like